Rahim. This is Jahangeer Soomro, Assistant Professor, Electrical Engineering Department, Sakharaib University. Now we are discussing Lesson 6 using Decision Making Structures Part 2. In this part, we are going to discuss Event-Driven Programming. So we will recognize basic features and functionality of event structures. We will understand event-driven scenario, what is the difference between polling and events, how basically event-driven programming works, how to configure the event structure, caveats and recommendations. So basically, event-driven programming is a method of programming where the program waits on an event to occur before executing the code written to handle that event. Basically, previously what we covered was the polling. In polling, the code is continuously checked to confirm that if anything occurred. So in polling, the code is continuously working, but this is not the case in the event. In event, it is basically on demand. So the processor will be in sleep mode and will remain in sleep until and unless an event has occurred. Alright, so what is basically an event? Event is an asynchronous notification that something has occurred. Event can originate from the user interface, external input-output, or other parts of the program. In this course, you will only learn about user interface events, which include mouse clicks, key presses, and value changes of a control. Alright, so let us differentiate between the polling and events. So basically, as far as polling is concerned, in polling, code is continuously checked. Here, you see in this polling, code is continuously checked. So loop must continually run to check if changes have occurred in the case of polling. And polling requires a significant amount of CPU time. So polling is basically CPU intensive. It consumes more processor time. And third thing, polling can fail to detect changes if they occur too quickly. So basically, polling is slower to respond and can fail to detect changes. Whereas, if we see events, basically, in events, they are on demand. The processor will be in sleep mode until some event has occurred. So, it reduces the CPU requirements of the program. So, it reduces the CPU work. And in events, events can handle all events in the order they occur. So it guarantees that a block diagram can respond to all interaction the user makes, handle all events in the order they occur, does not miss any events. So this is the difference between polling and events, and this difference will be further clarified when I will use this demonstration example. So you see, this is a simple VI, and here what happens that from here temperature is converted from degree centigrade to Fahrenheit, and whenever user changes the centigrade temperature, it will be accordingly converted into degree Fahrenheit, and whenever user will click time check, time will be displayed, and whenever user will click acquire data, data will be acquired. So how will you perform this activity? What can be the potential approaches? So far, You would only know how to implement this functionality by constantly polling the front panel controls. So see how you have learned to do it. So a while loop continuously polls the values of the control at the rate set by the wait until next millisecond multiple function, and I can execute the corresponding code in case structures. You see, it's a while loop. It will run continuously until user has pressed stop button. There are some case structures. In this case structure, whenever you click the temperature degree centigrade, if it is true, if it is false, then if temperature degree centigrade of the previous loop and current loop is equal, then nothing will happen. And if it is false, means user has changed the temperature degree centigrade, then it will be converted from degree centigrade to Fahrenheit. And this is get date time in second function, which will show the current time. And this is simulated signal sine waveform that you see whenever user clicks the acquire data button. So this is a simple VI that you can create by yourself. So this is the polling. Now one thing I want you to notice in polling, when I connect this indicator and name it to iteration, to show the iterations, alright, and let us remove this wait millisecond function and now run this. Now you see in polling, the while loop is continuously checked, it's continuously running, and you see iterations are being continuously performed. It does not go into sleep mode. And if you check the CPU usage, you will notice the CPU utilization is very high. In the case of polling, so you see CPU intensive usage is happening. So in this case, CPU is overloaded in the case of polling. So this is a drawback of polling, that loop is continuously being run, iterations are continuously increased, and there is an extensive utilization of CPU. So is there any better way? Yes, there is a better way, by doing the same work by using events. Let's try that. Now this is the same thing, but now this time this has been performed by using event structure. So you see, this is event structure and this is not the case structure. Later on I will demonstrate how to create this event structure, but so far now observe the difference. I create indicator here for iterations. Name it iteration. Alright. And run it. Now you see, unlike while loop, the code is not continuously being checked. It is on demand. The code will only execute only if the event will occur. Now see, whenever user changes the temperature centigrade, now iteration 1 has increased and the corresponding degree Fahrenheit is shown. Whenever user click time check, another event has occurred, iteration is increased by 1. Whenever user click occurs data, any other event has occurred. So the loop is not continuously being run. So this is the advantage of event structure. It reduces the CPU work. Now you see, CPU utilization is less in case of event structure. The CPU usage is very high in case of polling, but in case of event structure, CPU usage is low. All right. Okay. So this is the difference between polling and events. Also, you could see the difference by highlighting the execution. And creating indicator. Now you see continuously the code is, while loop is continuously running, something is continuously happening. Code is continuously being executed. In case of polling, when you turn on the highlight execution. Alright. But this is not the case in the event-driven scenario. You see, when I turn on the execution, nothing is happening. Nothing is happening. Only something happens when user clicks, when event occurs. Otherwise, the code is not continuously being run. So this is the beauty of event-driven, and therefore it is less CPU intensive. Alright, thank you. Okay. So, after understanding the difference between polling and event-driven programming, now we'll run this multimedia module to further discuss the event-driven programming. Alright.
After completing this module, Event-Driven Programming, you will be able to describe how event structures implement event-driven programming. Event-driven programming is a method of programming where the program waits on an event to occur before executing the code written to handle that event. An event is an asynchronous notification that something has occurred. Events can originate from the user interface, external I/O, or other parts of the program. In this module, you will only learn about user interface events, which include mouse clicks, key presses, and value changes of a control. With user interface events, you can design an application so LabVIEW generates an event each time a user performs a particular action on the front panel. Each time that event occurs on the front panel, the block diagram responds by executing the code you wrote for that event. Let's run this example VI. When I change the value of the temperature control on the front panel, an event occurs that triggers code on the block diagram to convert the temperature to degrees Fahrenheit and display it in this indicator. Similarly, there are other user interface events defined in this VI that trigger other code on the block diagram to execute, such as changing the value of the time check button, changing the value of the acquire data button, moving the mouse cursor onto the stop button, and clicking the panel close button. Now let's show the block diagram and turn on highlight execution. As you can see, user interface events on the front panel, such as ones demonstrated here, can trigger the execution of block diagram code that you wrote to handle each event. You should use an event structure to implement event-driven programming. You configure which events you want the event structure to handle. The event structure can have multiple cases, each of which is a separate event handling routine. You can configure each case to handle one or more events, but only one of these events can occur at a time. When the event structure executes, it waits until one of the configured events occurs, then executes the corresponding case for that event. The event structure completes execution after handling exactly one event. Click to select the Event Selector label.
This is Event Selector label.
The Event Selector label indicates which events cause the currently displayed case to execute. Click to select the Timeout terminal.
This is basically timeout terminal.
The timeout terminal specifies the number of milliseconds to wait for an event before timing out. The default is -1, which specifies to wait indefinitely for an event to occur. If you wire a value to the timeout terminal, you must provide a timeout case. If the event structure times out, it will execute the timeout case. Now, if this event structure waits 1000 milliseconds and no configured event, click to select the Event Data node.
So basically in this timeout case, if you select, if you create 1000 milliseconds, so if 1000 millisecond means 1 second, if up to 1 second nothing has happened, so this timeout case will be executed, and whatever you do in the timeout case, that will be performed after 1 second if nothing has been done by the user. So this is how timeout case basically works. By default it is -1, means it will wait indefinitely. So this is event data node.
The Event Data node identifies the data LabVIEW provides when an event occurs. The node provides different data elements in each case of the event structure, depending upon which event you configure that case to handle. For example, the Event Data node for a value change event includes old value. Click to select the Event Filter node.
This is event filter node.
The Event Filter node identifies the event data you can modify before the user interface can process that data. For example, clicking the Panel Close button on the front panel will normally close the VI. But this VI modifies the Panel Close event by discarding that event if the user clicks No in a dialog box. If the user clicks Yes, this VI will not modify or discard the event, so the Panel Close event occurs.
So these are the different parts of an event structure: event selector label, timeout terminal, event data node, and event filter node.
When using event structures, you should usually place the event structure inside a while loop. The event structure handles exactly one event per iteration of the while loop. You've completed this module. Here's a summary of what you've learned.
So basically, event-driven programming is a method of programming where the program waits on an event to occur before executing the code written to handle that event. And user interface events allow you to design an application so LabVIEW generates an event each time a user performs an action on the front panel. When that event occurs, the black diagram responding by executing the code. So use an event structure to implement event-driven programming. When using event structure, you should usually place the event structure inside a while loop. Alright. So configuring the event structure, you can select which events the event structure implements by right-clicking the border and selecting Edit Events handled by this case from the shortcut menu. In demonstration, I will show you how do you use Add Event handled by this case. Alright, and then you see when you click Edit Event dialog box, three window appears. But this is the configuring events. This is the configured event. This is the event sources, and third one is the events. All right. So in event-driven programming, one is the notify, another is the filter events. So you see, LabVIEW categorizes user interface events into two different types of events. The one is a notify, green arrow. Notify events inform you that a user action occurred. LabVIEW has already performed the default action associated with that event. But in filter event, which is denoted by red arrow, filter events allow you to validate or change the event data before LabVIEW performs the default action associated with that event. You also can discard the event entirely to prevent the change from affecting the VI. This is the difference between notify event and filter event. So here, before the LabVIEW performs the default action associated with that event, you can discard the event entirely to prevent the change from affecting the VI. Alright. So let us demonstrate how to create event-driven programming in LabVIEW. Alright. Okay. First, I am creating by using polling. Say suppose this is a while loop. Create control here for the stop button. Let us take case structure first. Okay, so whenever user presses this OK button, then what should happen? Take a one button dialog and type here user has clicked OK button. Alright, okay, run it. So you see user has clicked OK button. Whenever you click this OK button, this message will appear that you have typed over here. Alright, and whenever stop button is pressed, this code will stop. So this is by using polling functionality. So case structure is basically polling. Now, can we do it by any other better way? Yes, we can do it by using event structures. So how can I do it by using event structures? I remove this case structure. I go to structures and I pick up an event structure. All right, and then I right click edit event handled by this case, and in event sources I click the OK button. There are different options. In different way this event source can be configured, but for now I click value change, means whenever any change occurs in this OK button, then this event should be generated. Alright, click OK. What should happen? Whenever user clicks this OK button, press this OK button inside the event structure. So whenever user clicks the OK button, then this message will be will appear. User has clicked the OK button. And also in event structure, you should also create another event for this stop button. So take this again, click this, right click this and add event case and create an event for this stop button as well. And click here for value change. Alright. Take this stop button inside the event structure and then click it here. So whenever user will click a stop button, then this while loop will stop. Let us run it. When you click OK, then this event case will be executed and will show user has clicked OK button. And whenever user clicks stop button, this code will stop. Alright, this is how basically you create events in LabVIEW. Alright, so how can you, the next question is how can you program multiple events? I mean two events generated from the same event case. Say suppose I want two events to be generated in this same event case. Say suppose I take one numeric control here, alright, and then I want that either mouse enters this numeric control or OK button is pressed, this message dialog button should show the message, and here I am now changing the message that user has either clicked OK button or entered mouse in numeric control. Alright. Alright. So this is basically numeric control. How can I do it? I go to add event case. So I go to edit event handle by this case, and then I go to numeric control. I go to mouse and I click mouse enter. Alright. So now you see, whenever I enter the mouse here, this action will be performed as well. Okay. So you can basically you can configure two events generated from the same event case. Now let us discuss this timeout event case. Alright, so this timeout event case can be configured. Let us say I add another event case. I go to application and I configure this timeout case. And by default this is -1, means it will wait indefinitely. But now say suppose you want to create a constant here. Sorry, create constant here, and you want it to not wait indefinitely for infinite time -1, but you want it to wait for 3 seconds. 3000 milliseconds means 3 seconds. And after 3 seconds, this message should appear that, let us say, do something. So if user will not click any event, then timeout case will be executed after 3 seconds. See, now user is entered into this. Okay, all right. Now I'm not doing anything. After 3 seconds, this message will appear. Do something. Okay. If no event has occurred, then timeout event case will be executed. All right. This is all about the uh, timeout event case. Thank you. All right. Now let us move to exercise 6.2, converting a polling design to an event structure design. Okay. A little correction is required before moving to exercise 6.2, that if you want to configure two events generated from the same event case, so you have to click the edit event handled by this case and then add event and then numeric control and then mouse enter. So add event is necessary if you want to configure two events or more than two events generated from the same event case. Alright. So in this case you see, either you click OK button or you enter the mouse into the numeric control. In both cases this message will appear in the front panel. Alright, thank you. Now let's move to the exercise, basically exercise 6.2. So I open exercise 6.2, open the participant guide manual. Okay, so this is the exercise to convert a polling based application to an event based application and compare the difference in the performance. Description: first you observe the behavior of a polling VI. Next you modify the polling VI to create a more efficient event driven VI and observe the changes in the behavior. Finally you add different types of events to the VI. Table 6.3 lists the event you will implement, the UI event handler VI you create. So what are the events? If stop value change, stop the while loop. If time check value change, then display the time step when you click the time check button. Pen mouse down, display the coordinates of the front panel, point you click. Panel close handles that event in which user tries to close the running VI by clicking the window close button. So here the question mark shows that this is the filter red arrow and this is not the notify green arrow. Question mark shows the type of the event is filter red arrow. And then finally stop mouse enter. Whenever mouse enter, the stop button produce a beep when the mouse cursor moves over the stop button. Okay, now open the exercise and see the effect of the polling VI behavior. For this, go to exercise, events, open this Lavi project, open this polling VI. Alright, now run this. See, when you click the time check, you can see the time. Go to the performance. See here, when you run this VI, it is, notice that how high the CPU usage is. Utilization is almost 50%. Stop this VI, and now notice how the CPU usage drops. It drops from 50 to almost 28. Alright. Now go to the block diagram, turn on the execution, run the VI again. Now notice how often the time check terminal sends data to the case structure and how often the while loop iterates. So you see the loop is continuously running in the case of polling, as already discussed. Stop the VI, turn off the execution highlighting. Now modify this polling VI into the event VI. Now let us do it from beginning and from creating a new VI. Let's do it by ourselves. For this, you know that event structure is placed inside a while loop. Now take one event structure. Alright. Basically, this is the event structure. Alright. Go to the boolean, take this button, name it stop button. Alright. Okay, this is the stop button. Now create this event for this stop button. Go to edit event handle by this case. Go to stop button, click the value change. Now create constant here, take it inside the event, make it true case. Alright. Okay. Now after this, run the VI. And also, before running this VI, please connect indicator with this iteration terminal and name it iteration. Alright. Now notice that the iteration terminal indicator does not increment in the case of event structure, but in the case of while loop, it continuously increases because the code is continuously being checked. Switch the block diagram, run the execution highlighting. You see nothing is happening until something will happen only when event occurs. So event structure is waiting for an event. Click the stop button to stop the VI. Notice that VI stopped running even though the stop button is disconnected. Now you notice that this stop button stays depressed. This stop button stays depressed even though the mechanical action is, you see, mechanical action is set to latch when released, even though the mechanical action is set to latch when released. Even then, when you click the stop button, it stays depressed even though the mechanical action is set to latch when released. The reason the button stays depressed is because the VI stopped running after you click the button. Run the stop button by clicking it again. Alright. So how can we overcome this issue? Drag the terminal of stop button into the stop value chain event like here. Now run the VI again and click the stop button again. Now you see, notice that this time VI stops and the button resets and works like it should work under the option of mechanical action latch when released. Alright, now let us add another case as per the requirement of the code. So add a new event case, go to add event case, but before adding an event case, go to here, take a button, name it time check. Alright, name it time check. So go to add event case, time check, value change, press it inside the event structure. Alright, go to timing, get date time, seconds, and then create indicator to see the time. Alright, so run the VI. So whenever you click time check button, you see the time. Alright, see the see now the utilization of PC is good. It's almost 30, but in case of polling it was almost 50. So notice that CPU usage decrease when you use events instead of polling. Now stop this VI. Alright. Now let us add more notify events to the VI and add a new event case. This time create a mouse down event, go to the pane, into the mouse, click mouse down in the event panel, click OK, and in coordinates create indicator to see the coordinates. Notice that coordinate indicator displays the coordinates for each point you click. Notice that other events continue to behave as before. Alright, when you click, you see the horizontal and vertical coordinates of your mouse position. You see, other event case works as before. When you click stop button, this VI stops. Alright, now let us add filter events to the VI. Previously we added notify events that were green arrow. Now we are adding filter event, which is red arrow. So filter events allow you to validate or change the event data before Leview performs the default action associated with that event. You also can discard the event entirely to prevent the change from affecting the VI. Alright. So add a new event case and go to this VI in the event sources panel and panel close this filter red arrow. Event should be selected in the event panel. Click OK. Alright. Then in event data node, basically you can select source from the menu. Alright, you should now take two button dialog from the dialog in user interface. Take a NOT gate from the boolean. Connect the output of true button with this NOT gate and then create a message that are you sure you want to close the window? Are you sure you want to close the window? Alright. Now with the true button name, create constant yes, and with false button name, create constant no. Okay. File, save this VI and run the VI. Now click the close button in the top right of the window of the front panel. Now you see, notice that clicking the no button cancels the event and returns the VI. If you click no, it will return the VI. So this is the beauty of filter event, that it will ask the user and you can discard the event entirely to prevent the change from the affecting the VI. You see, this is not the default behavior of the LabVIEW. When you click this close button, it automatically closes. But when you click this, when you now have created filter event, it asks. If you click no, then no button cancels the event and returns to the VI. Clicking the yes button stops and closes the VI. If you click the yes button, this VI will be closed. Alright, stop this VI. Now add another event, last event, and then go to this VI, go to the mouse, enter. Alright, go to this mouse, enter, click OK, and then take beep VI. So basically what will happen, further edit this VI, edit this event handle case, go to the stop button and then go to the mouse and click mouse, enter. Alright, now whenever the mouse will be entered into this stop button, beep will run. You see, an event that produces a sound when the cursor is over the stop button. Alright, this is how event detector works, event-driven programming works in the LabVIEW. Now we have clearly understood the difference between the polling and event programming. Alright, let us move ahead. So what are the caveats and recommendations? Caveats and recommendations are that place only one event structure in a loop, use a value change event to detect value changes, keep event handling code short and quick, place Boolean control in terminals inside an event case for latch operations to work properly, avoid using an event structure outside of a loop, avoid configuring two event structures for the same event. Alright, lesson review. Which one of the following cannot be used as a case selector input to a case structure? Array cannot be used. How many events can an event structure handle each time it executes? 1. Which statement about event-driven programming versus polling are true? Events execute on demand is true. Event-driven programming is less CPU intensive, it is true. Event structure handle all events in the order they occur, it's also true. Polling may fail to detect change, it's also true. All A, B, C, D, true. Okay, thank you very much. We have completed lesson 6. Now in next lesson we will cover lesson 7. Alright. Thank you very much.